Hi guys, today we're going to be exploring a fun phenomena which involves a ping pong ball and a stream of water. Now, what do you think would happen if I put this light ping pong ball right here? Well, it is obviously going to fall, but what after that? We can clearly see that the ball is attracted to the center of the stream of water when I shift the position of the stream of water as it follows. It also vibrates vigorously on the surface. We can see that the ball stays on the wooden board even when I tilt it by quite a lot. This suggests that the force of attraction is actually quite strong. It can also vibrate on my hand. This is so cool. Now the question is, why does this happen? I've came up with 3 hypotheses. One of them I proved immediately wrong, the second one I proved wrong with a little bit of time, and the third one that I came to was finally, I think, the right answer. Don't quote me on this, by the way, I'm just a nobody who's not even that good at physics. By the way, the spirit of this channel is not directly telling you the correct answer, which you can probably get through a more reliable source, but rather to become your stepping stone on your way to finding the joy of discovery. My first immediate hypothesis was, can it just be the pure pressure of the water flowing down that presses the ball onto the ground, just like how solid does? Like that. To prove that a hypothesis is wrong, you would have to find something about the phenomenon that cannot be explained by the hypothesis. So there's a lot of things wrong about the hypothesis, and that is why it was proved wrong so quickly. One obvious mistake is that the hypothesis does not explain or state that there's any force that pushes or pulls the ball back to the stream of water, which you cannot explain why the ball can vibrate back and forth at the bottom. For example, at this moment right here, the stream of water is clearly not hitting the ball at the center, but the ball still managed to somehow move back and forth and continue vibrating. However, based on the model given by the hypothesis, if a solid exerts a pressure on the ball, which is perpendicular to the sphere's tangent, the force can be decomposed into a vertical force, which is counteracted by the surface below, and a horizontal force that pushes the ball beside. The missing component in the previous model is a force that pushes the ball back to the center. Now, the question becomes about explaining the force that is doing so. I realized that this force must be related to the property of water. And the first property of water that came into my mind is its free to change and random shape. The stream of water would surround the ball as it hits, and I believe that the layer of water exerted a force that was strong enough to push the ball back to the center. But this hypothesis was obviously wrong as well. See, it is not only water or liquid that can change its shape and surround the ball. Gas can do the same thing as well. We can conduct a simple experiment with a hairdryer. It can be clearly seen that there is no force whatsoever that has the strength to push back the ball to center. In the first place, the force created by the layer of water should be too weak to push the ball towards the center. Additionally, another major logical loophole in this hypothesis is that even if the layer of water is able to provide a pushing force, as the ball gets pushed away from the center of the stream of water, the layer of water that surrounds it should become thinner. Therefore, the force that pushes the ball back to the center is weaker. This means that the ball should not be able to vibrate this vigorously because it would be thrown away when the layer of water is too thin to provide enough force. As shown in the sketchy diagram, when the ball is away from the center and F2 is larger than F1, the ball should be pushed away from the center. To come up with a better answer, we should probably find the point of time of which the force first interacts with the ball. This is when the ball first contacts the water. Let's take a closer look. Now, I turn my focus onto another property of water, its surface tension. Due to the Coanda effect, liquid tends to be attracted to the nearby surface. In this case, the liquid below the ball, because of its surface tension, flows diagonally to the left bottom. This actually creates a force that pushes the ball back to the opposite direction of the flow of water due to the conservation of momentum. This force can then be decomposed into a vertical force that is counteracted by the stronger force of the water and a horizontal force that pushes the ball back to the center. It is actually very simple to prove this theory correct. As I move the ball towards the bottom of the water flow, the pulling force becomes stronger. This is because the stream of water becomes thinner towards the bottom, so more water can be thrown to the bottom left. Since momentum can be simply calculated by mass times velocity, an increase in mass would lead to an increase in momentum, therefore the ball gets pulled toward the center more dramatically. Anyways, thank you for watching today's video. Hope you enjoyed it. The answer given might not be absolutely correct, because I try to figure it out by myself. Anyways, if it is wrong, please tell me, and see you next time. If you find any interesting but confusing phenomena in your life, please tell me so that we can explain it together. Thank you.